Thanks everyone for your time to tune in to the webinar to find out what's new in ioGAS 7.2. There are lots of detailed changes in gas, but just in this in 7.2, but just in this webinar, we want to hit on some of the highlights. You know, it's a normal gas release. We have some big features and some new mathematical or analytics methods, and then numerous small usability improvements as well. But just in this webinar, we want to concentrate on a few of the bigger features. We'll touch on the detailed improvements later on, but as usual, everything is documented in the help file. So if you're wondering how to use something or what changed from the previous release, we always recommend people have a look in there. So some of the, I would say that the three biggest features in the release are the top three there on the PowerPoint. So classification and regression trees, or CART as it gets called, we've included that in gas, including the variant of random forest. The reason we put CART in, especially the classification trees, is that although the mathematics behind the method is complex, the visualization of the results are very visual and they're very easy to understand. And you'll see what we mean with that when we go through the demonstration. It's a supervised method, so it relies on knowing group memberships at the start to work out the tree. And then if you have unknowns, you can run them through the tree and predict their group membership. We also have a new data reduction method, which is TSNE, so stochastic neighbour embedding, fancy name, but really a way to think about how that works is most of the regular gas units that can be used to principal components analysis, using that as a dimension reduction technique, which is a linear method. TSNE is also a dimension reduction technique, but it's non-linear. It works in quite a different way. But really, it's trying to achieve the same end. It's trying to collapse multi-dimensional data into far fewer dimensions, like 2, so you can look at it on a screen or print it out on a graph, and you can look at the data to see if it forms any sort of natural groupings. One big difference between TSNE and principal components is it's only able to operate on the data that you've presented to it. The way the mathematics works, it means that you can't take samples that weren't included in the initial calculation and project them into the same space. So that's a bit of a weakness of the technique, but nevertheless, because it's non-linear, it can still reveal structures and patterns in the data that you might not have noticed looking at the raw data. And the third one there is that, you know, we know that people like using or projecting the mineral and rock compositions which are in the mineral and rock library in gas onto the various plots and diagrams that they're looking at. Well, now we've added the ability for people to add their own rock compositions. So, you know, if you have things like typical background rock compositions or typical rock type compositions or typical alteration chemistries derived or applied to different rocks, you can load them up into your own library and then just project them onto the diagrams and graphs that you're looking at to give you a frame of reference which is directly applicable to the project that you're working on. We've also made some adjustments to the regression tool, which we won't go into this seminar, but that makes it a bit more intuitive and easier to use. And there's now a link through to a new part of the IMDEX website, which is the IMDEX customer service portal, which you can go there and log tickets and bug requests and things like that. As usual, in case I don't come back to it at the end of the webinar, if you have any questions or if you have any feature requests or suggested improvements, please contact us, because anything or any suggestion that gets sent to us does get logged and goes into the mix, and we consider it for our next. Now I'm just going to go in and start up gas. Here we are. And I just wanted to show you a couple of things quickly, just to emphasize some of the different features of these new tools. So with the wait on, someone just told me they can't see the screen. All good? Okay, so I think we're back again. At least you can see the screen. So I just want to illustrate a couple of the features of the classification tree using that same data set that Putra was showing in the video. So I've gone into the classification tree here. And in case you missed some of the things when Putra was on his way through, here is the attribute manager. There are a number of groups there. So you can use the attribute manager to identify the known groups, just using the coloring in there. Or if you don't want to use the attribute manager, then and you've got another column in your file which identifies samples, then by all means pick that. Really importantly, regression trees or classification trees are non-parametric, so the distributions of the input variables really doesn't matter. The mathematics in the method picks the optimal set of binary decision points to classify the samples into their known groups, and then if you put unknowns in, to allocate an unknown into one of those groups that you use to build the tree in the first place. This makes it almost completely different to every other multivariate method, supervised or unsupervised, that's in GAS. Now, I've already picked a selection of variables to enter into the analysis, which you do via the variable selector as usual. And using this method, the way I'm going to classify, I'm going to build the tree, and the way I'm going to classify unknowns in this case is just to have them in with the known samples, but just leave them unselected so they won't participate in the building of the initial tree. So I'm now going to go in and I'm going to train the tree, just build it in the first place. If you really want to check the veracity of the model that you're building, you can partition the data into training and test sets and keep running it to test the stability of the tree. But here I'm just going to use all of the data to train it. And there it is there. And one way I often use to describe how these things work, it's a bit like one of those clown heads at the show where you pop the ball into and then it drops into a slot as the as the head rotates. It's a bit like that. So if we were to drop a sample onto the top of this tree and the nickel concentration was greater than 269, it would head down that branch and be immediately classified as a silica carbonate ironstone in this case. If it was less than that, it still doesn't know where it belongs, so it would use another decision. And if the lead was greater than 4,150 ppm, then it would drop into that slot, the Kuroko. So it's a really, really nice visual way of illustrating how your samples are being classified into those known groups based on the input variables that you're using. Chemistry in this case, but it doesn't have to be chemistry. But just remember though, these terminal nodes, as they're called, can reappear more than once. That's just the way that the maths works. If you're wondering which groups are being easily classified for the method and ones which have some input samples which don't go into the right group, you can open up the confusion matrix and have a look in there. So for example, 9 of the 11 fault copper ironstones are correctly classified, but 2 of them get confused with the Kuroko group. So it gives you an idea of how, if the classification efficiency is not 100%, then which groups have a greater problem with their classification. You might need to go back to the training groups in that case. And another bit of very useful diagnostic output is the way the method works is it outputs a variable importance column like this one here. And so what this is telling you is that I've put in 12 or 13 input elements into the method, but it's telling me that to achieve that level of classification efficiency, it only needs to use the top 4 or 5 elements. That's all it needs. It doesn't actually need the other variables to classify things. So often, if you're running one of these complex methods, sometimes the output illustrates you the easiest way or the most simple way to convey the results to your work colleagues. So it often points you at what is really the essential information of the data and really what is extraneous. So I'm just going to close that now. Now, if we've brought our unknowns in with the training data, we can now classify the unknowns while we're still in this workflow. You don't have to do it that way. You can actually save the tree and apply it to a new data set later on. But this is a pretty easy way of doing it. And the way we run the unknowns down the tree is to use this button here. So what it's saying is run the tree on the invisible rows. So that was that group of 4 samples, or 8 samples, 4 I think. And when I click it, what it's telling me, so there were 8 of those. So 8 samples have gone into the tree and they're gone to that node, to that node, to that node, to that node, and then being classified into the Cypress type. So this is a VHM Gossamer training group. They're being classified into that Cypress group, and you get a little highlight that runs down there. So that's a pretty cool way, actually, if you've got good training data, of allocating your unknowns into one of those training groups. Of course, if the unknowns you're trying to classify don't belong to one of the training groups at all, then just beware and do a little bit more analysis of the data before you use it like that. So that's that's a really neat visual tool, and it's really also very good because it doesn't rely on input data transformations. Now, I'm just going to close that and go to the other new multivariate tool, in this case the TSNE, and here's the dialog, as you saw before with Pootra's video. Now, we've included quite a few methods in here, so there's 2 different libraries. When you look at these different methods, there's always many different implementations of them, so we've included a few. But the default selections here, what we think are the best algorithms to apply TSNE to geochemical data. But if you want to get into it and research it, then by all means change it. It's a very computationally intensive method. So this Barnes Hut has a couple of clever things in it to speed it up, and the Barnes Hut parallel has some additional ways of parallelizing the computation to speed it up even more. So if you're running really large data sets, then just to have a bit of an experiment with those. There are some additional parameters in here, so perplexity and theta, things like that. I just recommend you have a look in the help file. But again, because it's gas, we've put starting values of these, which you think are okay most of the time. A really important box in here, which you must look at, is transform. Now, part of the TSNE calculations involve the calculations of Euclidean distances between samples. So the distribution, the center, and the range of your data is very important and will influence the results radically. So to help people out here, we have our normal input transforms, but we've also concatenated a few of them to try and get the data under control before you run it. So for example, here we take the input data, we'll take the log of it to change the shape of it, make it more symmetrical if it's got a long tail to the right. Then the Z-score to equate the centers of the data, and then we scale the range from 0 to 1. So I'm going to pick that and then go OK. Let's just pop behind the window there. It's going to overwrite 2 of the columns. Go OK. So in this case, it's output 2 columns. And again, this is the same data set. So you can see here that it's really illustrating that there is, essential structure present in the data, which illustrates that the chemistry of these gossets does form itself into groups. So if you didn't know the a priori group membership and you just ran the data through this, you'd look at that and go, oh, there are some significant influences in the data, and maybe I'm going to go and look at that. And you would circle some of these and see where they plot in space and things like that. But just to illustrate the importance of the input transformations, I'm just going to run it again and just say nothing and just leave the input variables as they are. And being Gaussian data, the data ranges over wildly different scales, and most of it's long tail to the right. But if I don't do anything and just hit OK, again, it's going to overwrite. We get a result there that looks like nonsense. So, caveat emptor, buyer beware. When you run this method, you need to think about running it like you would with a PCA and look at the condition of your input variables before you hit the go button. Now I'm just going to hand the screen over to Pootra, and he's just going to run through putting your own rocks into the rock library, because that's also an important new feature, and it's worth dwelling on that a bit. Then we'll come back and finish off. Here we go.
Hey guys, so I'm just gonna run through exporting your own user nodes out of ioGAS. So for a bit of context, what I'm going to be talking about now is the ability to basically add your own minerals or rocks into a new tab in the minerals and rocks library window. So just before I touch on that, I'll just let you know that you can resize the window, which is a pretty cool new feature. Um, so we provide a template of the new user nodes as a new separate tab. And that's important because every new tab that you generate will be present as a new top level tab here. So there are two ways of exporting your own user nodes, as I was showing you in the video. So the easiest way, and that I would recommend, is if you already have your data in GAS, present as columns and columns of geochem assay, and you have all your information and things like that. The best thing to do is to click on the user nodes option from the file ribbon bar. And by clicking on that, it'll take you to this dialog. And by default, it will export only the visible rows set in the attribute manager. So as we have it here, I have all the rows set to visible. So this is good if you want to export pretty much your entire table of data out as user composition nodes. But in this case, I only want to export, say, just the first group in this list. So I'm just going to turn everything off, except for the top copper Gaussian unknown group. So this is the same Gaussian data set that Dave was showing earlier on with the TSNE and with the classification tree. So I'm just going to export this group, which is the only one that's set to visible. So the best thing about this tool is that it takes in all your geochem assay, and what I was showing in the video just then is that the table has everything in the format of weight percent for all of the assay columns. And if your data is in ppm, a combination of ppm and oxide, it'll do the automatic conversion on the fly in the background. So the outputted column will be automatically in weight percent, and that's a really good thing, because if you want to edit this user nodes file manually, you have to make sure that everything is in weight percent. So in this dialog, so I'm just going to run through it pretty slowly. So the tab name is obviously what's going to be displayed in the top level. So I just call this copper Gaussian export, and group is what is going to be just the second level. So just the one level below. So we're just going to assign a deposit as a group, and I'm just going to assign a deposit for the description and for the name and short name and description. So the last three will control how it's going to be displayed within the selection dialog and also within the user nodes itself when you plot it up on a scatter plot, for example. So let's just do this for now. And it will export all of these points as rows in a user node file. And so let's see what it looks like. So the new user nodes, they will be exported. They will be exported as a user node format file. So let's see what the file looks like. So this is the template that ioGAS ships with. So basically we are able to just edit this file using our own user node, for example, and you can use this as a starting off point, and of course you can do the method that I described earlier. And so what we can also do in this style in the exported file is you can edit this out. So you can say, you can make the changes here as necessary, and description is also what's going to be displayed in the dialog and within the plotted node. So I'll just say U1, I'll just as a test kind of thing. I'm gonna save this. I'm gonna bring it to GAS. So it's automatically brought into ioGAS once I already save it. So it's already basically brought it in as a new tab at the top level. And one thing is, if I make a change to this, so if I want to make everything the same group and save the Excel spreadsheet file and I click reload, it'll apply the changes automatically to the group that's already present in the exported tab file. So that workflow is pretty straightforward. So you export it using the data that you already have in GAS, and you export it as a spreadsheet, and then you open it up, and then you do the metadata editing. So, and you don't have to touch on the assay columns again because they've already been exported out, right? So all you need to do is just make sure that it displays however you want it to be, and then you can control how it looks within the dialog, and you can control how it looks when you plot them up in GAS, and you'll see that the changes are reflected in both the dialog and with the plotted points as well. So 2 ways, and I would recommend exporting it first and then do the metadata editing, or you can do the other way around by editing the template that we provide. And yeah, that's pretty much it. I'll give the control back to Dave.
Thanks, Pooja. So thanks for attending that, and thanks, Pooja. So just some other some other improvements that we won't go into, and they're myriad. So you can now append a GAS file rather than just CSV or Excel files to an existing GAS file. We have Windows authentication if you want to link through to a SQL database. There's some improvements to the user interface, and also the wavelet tessellation tool, which we know has been very popular since it went out. Just on the second page here, some little modifications. So in biplot specifying the rendering order, the resizing the dialog for the mineral rock nodes is an important thing. We know that used to annoy people, and we've split up the analysis ribbon a bit too to make some of the analysis tools easier to find and to guide people's use of them. So that concludes the webinar. Like I said, we will record this and put it up on the website if you want to come back to it or share it with your colleagues. But as always, any questions, always contact us through the help system, and we'll respond to you. So thanks for your time, and we'll see you around the traps.